Hope you guys are excited for something new and fun. We're going to try middle of the night physics here because the kids are sick, so I'm gone today for you. So I'm going to try and teach you center of mass kind of through a video. So let's see how it works. So, first thing to start with, center of mass is kind of an interesting way to solve a problem, mainly because if I look at Newton's third and second law, we see that if there's no external forces on the system, there's no acceleration. What that means is that object is going to experience the same thing it would as if it was just by itself, whether it was multiple objects or just a single object. Let me give you an example. So let's say I was shooting a ball. That ball flew through the air in a nice parabolic path and landed over here. Let's say instead I loaded that ball with, I don't know, dynamite. And here it goes, and when it gets to this point, it explodes. Okay, so now I have little chunks of ball moving in all different directions. All right, there we go. I think it blew up into enough pieces. How it turns out is the center of mass of all those different pieces actually continues along that parabolic path, even though all of those pieces are going in many different directions. Okay? And so we're going to use that trick to solve these problems. But first we need to know, how can we find the center of mass of multiple particles? So that's what we're going to look at first. So this section here deals with finding the center of mass of multiple objects or points. Over here, this is when we have an object that's not uniform. Think of a baseball bat. One end of the baseball bat is thin, and so it doesn't have a lot of mass. But as we go toward the other end of the baseball bat, where it's thicker, it has more mass. So rather than the center of mass being exactly in the center of the object, it's actually skewed to one side. And so this equation will help us figure that out. All right, so for multiple objects, it does have this r vector in it. Okay, so an r vector, that is going to have components. So here might be my r vector at an angle theta, think polar coordinates, and it is going to have an x component and a y component. All right, so in other words, when I find my center of mass, I'm going to do it with a x component and a y component, and so my center of mass will have an x and a y component. Sometimes our objects will be lined up in a nice line, so maybe 2m, m, and 4m. And I say, well, if these are separated by a distance of 1.2 meters, this is separated by a distance of 2 meters, where is the center of mass located? And you might be able to tell me that, here-ish? You don't know. You could probably make a guess, though, that it's somewhere near the center. Maybe a little heavier toward the 4-meter side. But this is going to allow us to figure that out. Here I only have x components for my r, though. But maybe instead I have 3 masses in a triangular formation, m, m, and m, and it turns out that all these m's are on the sides of an equilateral triangle. The center of mass is going to be right at the center. And we would be able to figure that out by averaging the x components and the y components of those objects. All right, so let's try some of these. So we're going to turn to page 50 or 272. Yeah. All right, so let's start with a little picture here. So this is, again, number 53. All right, so here's Pluto, and it has a radius. We'll call it radius of Pluto. And then there's a distance out here, and then we have Charon. Not much smaller, but it has a radius for C. And again, this is Charon. And we want to find the center of mass. Since they're pretty similar in size, not terribly different, oh, I guess maybe this one's maybe a little bit smaller. It's a video, Mr. Foster. Just move with it. It's the middle of the night. Shh. All right, here we go. So it's a little bit smaller. Well, so I'd say the center of mass isn't going to be in the center, but rather maybe off to one side. Okay, so let's see if we can figure out where this location is. All right, so we're again using our multiple points or multiple objects center of mass. Okay, nice thing is they're on a line. So I'm going to call this point x equals 0, and I'm going to call this the location of Charon, which it tells me is, what was it, 19,700 kilometers away. All right. So I know the locations of my two masses. Now I just need to know their two masses. Now, unfortunately, they did not tell me the masses. Instead, they told me the radius of Pluto was 2370 kilometers, and the radius of Charon was 1250 kilometers. All right. But they did say that they have the same density. Oh, okay. So I'm going to have to use density. I'm just going to hope that stuff's going to cancel out. I got masses on top, masses on the bottom. So let's hope those densities cancel out for us. So spheres, they're roughly spherical. So the volume of a sphere, 4/3 pi r cubed. If you knew that, get yourself a gold card. All right, now we're going to move on. So mass is equal to density times volume. All right, so if I use my R center of mass equation, and these are all in the x direction. So again, our positions are only going to have x values. Our y values, since none of them are in the y direction, our y values are going to average out to 0 along that x-axis. All right, so I have the mass of Pluto times the position of Pluto. Guess what? It's 0. So that goes away. Plus the mass of Charon times the position of Charon. That's that value right there. All divided by the mass of Pluto plus the mass of Charon. Okay, but instead of mass, I'm going to use this density times volume equation. Okay, and again, volume is 4/3 pi r cubed. So RCM. So I have the mass of Charon. Oops, but we're going to make a substitution there, aren't we? So we're going to call it the density times the volume of Charon. So 4/3 pi times the radius of Charon cubed. All right, times xc. All right, all divided by the density times 4/3 pi radius of Pluto cubed plus density times 4/3 pi. Oh my goodness, so much stuff is going to cancel. RC cubed. All right, so let's see here. Density 4/3 pi, density 4/3 pi, density 4/3 pi. Oh my goodness, everything canceled. Wonderful. So I'm left with the radius of Charon cubed times xc, all divided by the radius of Pluto cubed plus the radius of Charon cubed. All right. So now we're just going to plug in those numbers that we have up here, and we're going to get an answer. All right, so let's get out our trusty calculator here. So we have, and I'm going to leave them in kilometers because if I have all kilometers, guess what? Kilometers are going to make kilometers. So we'll leave it all like 20 kilometers. Again, if we would have changed them all to meters, it would have worked out the same kind of way. All right, so we get 2520. Well, the radius of Pluto is 2370. So it's actually located right about here. Just outside is the center of mass. So what that means is that if I looked at the path of Pluto and Charon, this would be its center of mass path. But in the process, what happens is here is Pluto, over here is Charon. And what they do is they actually kind of rotate around this point. Okay? So if I was to kind of draw the next position, so here's my center of mass, Pluto might be located here. It's a little bigger than that. There it goes a little better. And then here's Charon out here. And so again, Charon has just moved this way, Pluto has moved this way. And they're just kind of continuing on. And so here's Pluto, here's the center of mass, here's Charon. And they kind of orbit around this point here. And it's the fact that Pluto has not cleared its space and dominated its space that makes it not a planet. It needs to really dominate. So one of two options. It could just go ahead and just kick Charon out of there somehow. Or Charon could get smaller, something like that. But we get that kind of result that Pluto kind of orbits that center of mass, and Charon also orbits that center of mass. And they kind of both follow the path of the center of mass that also orbits the sun. Okay. All right. It does show that we have a clicker question. We're not going to do that through this video, unfortunately. I think I need another piece of paper, but we're now going to try the situation where I have an object that's not a continuous density, or not a mass that's uniform, like a rod or something like that. So I'm going to try it with a baseball bat. All right. So this equation, instead of just adding up individual objects, essentially I'm adding up all of the little points of mass over a distance. Well, adding up over a distance. Okay, we got ourselves an integral. And we're going to end up with something called a linear mass density. This describes the mass as it changes with position. So if I look at my baseball bat, the mass starts small, because there's a little mass right here. Of lead. Oh, there's still more in there. Come on. Come on. There we go. Someone would be throwing me a marker at the moment, but I just have a pencil. So right here, the mass per little distance, delta x, is quite small. But over here, because it's a little taller, that mass per delta x is bigger. And so I can generate a function to describe how is the mass at each position. Here it's a small number, here it's a big number. Okay, so let's find the location of the center of mass of a rod with a length L and a linear mass density of 4x squared. So this value right here is that lambda value. Okay. So, or my mx, which is located right here, mr. mr is just a three-dimensional variable. Mx is more of a one-dimensional variable. The AP test is only really going to be one-dimensional for this situation. We're not going to do a two-dimensional freak show on you. All right, so we're going to go ahead and solve that. Is this all on? Yeah, we're good. All right. So here we go. RCM. So I'm going to take the integral from 0 to L. Those are my bounds for my rod. It has a length L, and it has a R, so an x, because we're one-dimensional again, times my lambda, my mr value, 4x squared, all in terms of, or take the integral with respect to my x value. Again, we're just doing this one-dimensionally for now. And then from 0 to L of 4x squared, my mx value, dx. Okay, so let's go ahead and solve that. So I have really x cubed here. So it's going to become x to the 4th divided by 4, which cancels out that 4, evaluated from 0 to L. On top, on the bottom, I'm going to have 4 divided by 3, x cubed, evaluated from 0 to L. So you can see my zeros are going to cancel out stuff. That's wonderful. So I'm just going to be left with L's. So RCM equals L to the 4th divided by 4/3 L cubed. Obviously we get some L's that cancel. And we're left with 3/4 the length. And there's my answer for a situation where I have a linear mass density that changes. All right. I'm going to go ahead and end this video and start a new one, just so it breaks it up.